Good afternoon, everybody. I'm Gianluca Speranza. I'm a PhD student at Laboratory for Soil Mechanics at EPFL in Switzerland. My supervisor is Professor Alessio Ferrari, Professor Lias Lalui, and Dr. Pierre Lassalle. The title of this presentation is Physical and Numerical Modeling for the Sustainability of Retaining Structures in Unsaturated Soils. Regarding the research context in this project, I'm working on the optimization of technical and environmental performance of geostructures. In particular, with the EPFL, we have studied the interaction between unsaturated soils and geostructures, and with the industrial partner Novotec, we are evaluating the impact due to the construction of this kind of geostructures through performing life cycle assessment analysis. When we talk about unsaturated soils, we know that almost the 33% of the earth is considered arid and semi-arid, and the 60% of the world's population lives in area where the soil is unsaturated up to several meters of depth. But if you think how we design this kind of retaining structures, we only consider the soil either totally dry or totally saturated. Actually, we have that the soil behave in a different way. We have that during the infiltration we have an increase of the pore water pressure, while during the drying period we have a reduction of the lateral air pressure. So the main question that I started to ask to myself is, first of all, can we rely upon suction? I've heard before that we cannot rely, but I will say that it depends. First of all, in the what kind of soil we are taking into account, and also we have to consider the intensity and the typology of the rainfall events. Another question is, are we already relying upon suction? To this question I would answer yes. For example, here there is a building construction site where this temporary retaining structure is relying of the suction, and just on top they will put some plastic tower to keep the suction behind the, to keep the suction behind the retaining structures. So when we approach to this kind of problem, it is really a difficult problem, because we have in this study a soil structure interaction problem. There is the mechanics of unsaturated soils, so there is a full coupling between the hydraulics and the mechanics of the soils. So we decided to approach to this problem with three approaches. So starting from analytical analysis to see in the literature what are the effects of the rainfall events to the lateral air pressure distribution, performing both steady state and transient analysis. Of course, this analysis is a simplistic one, because we do not consider the constitutive model. There are some limitations regarding to the water retention behavior of the soil in order to have closed form analytical equation, and there is no validation of this kind of approach. For this reason, we decide to investigate the problem from an experimental point of view by building a physical modeling in laboratory, and the third part of my PhD, in which I'm most working on now, is the numerical analysis, where I'm studying the coupling between the hydraulics and the mechanics of the problem, simulating the rainfall events. Let's start from the beginning. We have the analytical analysis. So in the literature we can find the extension of the Rankine theory, considering the mechanics of unsaturated soils, by performing also seepage analysis. And we can see here that the water retention behavior play an important role in terms of degree of saturation, in terms of volumetric water content, its evolution with the in the space and with the time, and the matrix action. Moreover, the volumetric water the water retention behavior play an important role in the on the shear strength and its evolution with the time, and moreover we need to well characterize it in order to have the resolution of the Richards equation to see how it's changing the matrix action during the rainfall event. The same approach can be also presented in limited equilibrium method. For example, here we have the Coulomb method, and for this reason what we did, we start simulation of the test, considering of this analytical methodology, considering three types of soil: a silt soil, a clay silt sand, and a sand, where we have starting from the water retention behavior and the hydraulic conductivity, we have performed the analysis that I was discussing with you, and we see how is changing the degree of saturation and the lateral pressure with the increase of the infiltration rates for the silt, the clay silt sand and the sand. First things that we can see is that we have an increase of the degree of saturation with the infiltration, and we have the total disappearing of the matrix action when the infiltration rates is set equal to the saturated hydraulic conductivity of the soil. And the effect, the lateral pressure, we can see that is changing, is increasing with the increase of the infiltration rate. Here you can see with the increase of the infiltration rate, while for the silt the phenomenon is more evident, while if we consider on sand, the effect is almost negligible with respect to the condition of dry one. Another thing that I would like to highlight here is that we have, if we consider, even if we are considered the worst scenario has the infiltration rates equal to the saturated hydraulic conductivity of the soil, the lateral pressure is almost the half of considering the soil totally saturated with groundwater table at the top. We extended also this approach to the transient condition to see how long do we have to wait up to we will have the total disappearing of the matrix action. For the silt soil, we have to wait, setting an infiltration rate, a boundary condition equal to the saturated hydraulic conductivity, we have to wait 600 hours, while for the clay silt sand 100 hours and for the sand 24 hours. Of course, behind this problem there are some limitations. There is no experimental validation. For this reason, we start to model this phenomenon in laboratory with a physical model. This is the model of the that has been designed and built at the Laboratory for Soil Mechanics. It's a fully equipped model where we have it's equipped with high capacity tensiometers for the recording of and the measuring of matrix action. There is a water-filled hydraulic cylinder on the back of the model, and one of the wall of the box is made of glass to perform particle mass invelocimeter to see what happened to the failure surface. So here there is a video. Then here we designed the support for high capacity tensiometers that are a dynamic tool that help to easily remove the tensiometer in case of cavitation. And this is the material, the dimension of the box, that is 1000 millimeters of weight, and the active part of the wall is almost 500 millimeters. The water-filled hydraulic cylinder is made of inox steel because he has to be, it is to work with water and is connected with a pressure water cylinder. Moreover, what I would like to highlight is that with this dispositive we can measure the horizontal component of the lateral earth thrust. This here I'm explaining the experimental phases. The first one is I performed the experiment considering the soil totally dry, imposing a displacement to see what happened to the failure surface. Then I put the soil in unsaturated condition through the capillary rise to see what happened to the failure surface in this condition, and the next step that I'm working on is the evolution of the lateral thrust with the performing of some infiltration. For the moment I'm focusing on this kind of experiment. So the experiment consists of to have the box at the beginning that is empty. I'm controlling the volume inside the cylinder. I got the box filled with the material, and then I was applied the displacement and was recording the force and to see what happened. During the rainfall events, I decide to do it in at-risk condition, performing the infiltration and understanding the changing in the pore water pressure, performing some cycle of infiltration and evaporation of the water. So to do it, of course, was needed to do the calibration of the system. It was done with applying a force or changing the volume inside the hydraulic cylinder. And the first things that I did was and that I observed was that the behavior is not symmetric, so I need the two calibration curve in terms of loading and unloading. This calibration has been done at constant volume and with controlling the pressure inside, so allowing the volume to change, as can be seen here in the charts. The same things has been done considering the variation of the volume and the relation with the displacement, and in order to have a better, in order to have a measure of the displacement and the correlation with the volume inside the cylinder. Then I did the numerical simulation of the retaining wall in order to achieve, to see that the deformation of the wall was lower compared to, so the stiffness of the wall was higher compared to the one of the soil, and moreover this analysis was helpful to achieve the bending moment and the shear strength at the base of the wall for the design of the linear guideways. Here we can see that was a need to put some reinforcement because there was the deformation was too high on the two sides of the wall, and the bending moment and the shear strength at the base were helpful to design the linear guideways that are a special tool that allows to have a solvent friction between the this tool and the railway part. So in this way we can reduce at minimum is possible the friction. Then we have also built high capacity tensiometers in collaboration with the University of Strathclyde. I would like to thank Professor Alessandro Tarantino and Roberta for sharing their knowledge with us. So it was a great experience to build the high capacity tensiometer that are working pretty well. And I would like to thank them also for the assistance during the construction phase for both the tensiometers and the saturation jumper. One experience that I liked a lot was this first saturation of the high capacity tensiometers, where I was putting the tensiometer in this special tool and this box. When the tensiometer was drying, I was removing the air, applying creating the vacuum inside from the valve A while the valve B was closed, and at a certain point I closed valve A and starting to open valve B, injecting the water inside. This phenomenon was recorded, and as can be seen here, we got the evolution of the voltage in the tensiometers. We got at the beginning the tensiometer was dry, then we started to apply the vacuum inside for almost 15 minutes. At a certain point we started to apply the water pressure, and we see that the ceramic of the tensiometers were started to be saturated up to arrive to the here we got the total saturation of it. At a certain point we reduced the pressure, we got a constant volume, and then we start again to apply the water pressure. We can see here that the curvature is totally different respect to the initial one. After a cycle, three or four cycle of this, we can assume that the tensiometer was saturated. Then we got the test of the cavitation, and we are very happy to achieve the classical shape of the cavitation of the tensiometers. We used also the tensiometers for the characterization of the water retention behavior of the SILT. Moreover, these two material were the two material that has been tested in laboratory for the physical modeling. For the moment, I performed the test with the sand. I'm working on the SILT, and now we can see the characterization of the water retention behavior for the SILT. So what we did, we took different specimen of sieve, free specimen. This is the apparatus that allowed to characterize the water retention behavior. We have the saturation chamber with high capacity tensiometers. Free specimen were used. The first one was put in contact with the high capacity tensiometer for the recording of the matrix action. The second one, assuming the that were created with the same initial void ratio, was placed on the scale to measure the change in the mass of the specimen due to drying and wetting path. From the top there was some recording of the picture to observe the deformation of the specimen. So we started the test with the soil that was totally saturated through capillary rise, where infiltration was prevented from the top. Then we started with the test of just putting the soil in contact with the atmosphere. So we start to have a increase of the matrix action recorded with the tensiometers, and as can be seen in the drying time lapse, deformation plays an important role. We can see how the soil is shrinkage during the increase of the matrix action. And we performed the same test in both continuous drain path and in the wetting path, but this was the wetting path by steps, because we started to wet our material up to we got that during the wetting we have a reduction of the matrix action. The evaporation was prevented in each step, and then we go up to we got the equilibrium, and then we started to wait again up to arrive to the initial condition. Also here we have the wetting lapse, where we can see the swelling of the, it's clearly visible the swelling of the material with the creation of some bubble of the top of the sample due to the presence of air inside the specimen. So from the top it was possible to record with a 2D photogrammetric technique the variation of the diameter, and making the assumption of isotropic behavior, so that the radial deformation and the vertical one were equal, it was possible to estimate the volume changes, so in this way achieve the water retention curve in both in terms of drying and wetting path. Moreover, it was possible also to achieve the shrinkage curve and the swelling curve. The shrinkage curve was achieved in we can see that first of all the shapes is in agreement with other results found in the literature. For example, here we can see the results provided by Professor David Toll in 2015. And we also got the swelling curve, and moreover we can see that all the deformation happens before their entry value, and then we are at the shrinkage limit. We were not satisfied about this kind of results, first of all because we have some holes here, and also because we arrived up to 1000 kPa, and then I was worried that the tensiometer could cavitate. So then we combine, we use a third specimen, we combine, we started to monitor a third specimen where resuction was recorded using a WP4C apparatus. In this case we are talking about total suction, but we making the assumption that the osmotic component is negligible, and that is validated when we can see here the results of the tensiometers and the WP4C apparatus was almost the same. So in this way we could arrive up to the residual degree of saturation, starting with the wetting again. So we could characterize the water retention behavior and achieve the parameters for the Van Genuchten parameters in this case. For the sand, the results were different. We cannot use we decided to characterize this kind of material by performing here first the granulometric curve of the material, then the Pycnometers test to achieve the specific density, because it's very important in the physical modeling due to the level of stress that you have at that scale, and also the evolution of the density with the degree of saturation. Then we achieved the water retention behavior of the sand by applying the engine negative water column technique. So we create different specimens in the pressure plate apparatus, and we were imposing the suction by reducing apply the suction by reducing this 8. In this way we were sucking the water from the sample. By this approach we can see that we performed the test in drying and then in wetting by rising up the burette, and we got that the entry value of this action is almost 3 kPa. Here we can see the cycle in terms of drying and wetting. As confirmed, we cannot achieve again the full saturation because there was some air inside the specimen. Another characteristic test that we did is the direct shear test at very small vertical stress, because in the physical model you know that the level of stress is not so high, so we have to take into account that the envelope of the failure criteria is not linear, but there are some curvature. For this reason we have that in this level of stress the shear strength finger is very high compared to the one of the condition. We can say that actually we are not so far from the one that we have for retaining wall that have a height of 2-3 meters height, compared to the condition of to have a diaphragm, for example, that we are in another situation. So we did the test by using advanced shear test apparatus, and tool that was built by where the stress was applied by powdering sand inside a box here that was applying the shearing, and from the top there was a box that was applying the confining. So as is confirmed from the results in the literature, we got a shear strength angle that is very high. We have 52 degrees of peak that is reducing with the increase of the vertical stress. Here are represented both in terms of peak and constant volume shear strength angle. Here I performed the test with the model that has been built. You can see here in this video, this is the soil totally dry. You can see here the evolution of the failure surface that is clear here. And then we started to analyze the results. I did the test 2 times to see that we have the pressure, and that is with the calibration curve is correlating to the force. We have a reduction of the course, so we are reaching, we guess that is here the active state, and then we arrive to the residual condition. So we did the test 2 times, and we were pretty happy to achieve the same results. And maybe we could assume that here is the active state, but we will see from the digital imaging correlation what happened. So first of all, I decided to highlight that there are side effects on this part, because there is a curvature in the failure surface here, but there is a huge part that is acting directly on the wall. So for this reason, the box has to be, when performing this test, really the dimension of the width has to be really high comparing to the height of the wall. Then we started to do the digital imaging correlation to observe the failure surface. First, we did sensitivity analysis of for the mesh of the analysis. The digital imaging correlation allows to detect some pixel in different picture, and following this picture it's possible to achieve the displacement field. So from that achieve also the velocity if we provide the variable of the time. So we choose has a dimension of the sides 32 per 32 pixel for the sides and for the spacing, and we got here first of all what happened in the first minutes, and we see that the failure surface started to be present between 20 and 30 seconds. That was exactly the point where we got the curvature in the figure that I was showing you before. Then we got the evolution with the time of the failure surface. Here there is the average. We can clearly see the position with the failure surface of the soil totally dry. In terms of vertical displacement, horizontal displacement, and this is the combination of the two that maybe is the one that we should look at. Then I did the same test, but this time with the unsaturated condition. So what I did is that I was controlling the level of the groundwater table. We can see here with this box container. Then I started to fill the box, almost 1 day to fill it. And then I was observing the capillary rise. To be sure that what I was observing here was the same, I put also this glass column in the back of the back part of the box, and I see that the capillary rise got the same that I was recognizing on the front part. What is really important, I was really surprised to see this result. Here you can see during the filling the increase of the capillary rise. I was controlling the level of the groundwater table that reached almost the half of the retaining wall. And you can see that there seems to be a correlation between the increase of the capillary rise and the reduction of the pressure behind the wall. Especially here between the point E and F, you see that there was no increase of the capillary rise. That was the same recognized here in terms of pressure that seems to stabilize. Then I put in contact the tensiometers in the part of the soil that is in unsaturated condition, and I got a measure of the suction in terms of with the tensiometer, starting from the condition of tensiometer in free water. Then I put the tensiometer in contact. There is this jump due to the installation of the tensiometers, and then the recording through the test that was the same, up to arrive to put again the tensiometers in the free water. Here there is the results of I started to apply the displacement of the wall, and we see that the force is significantly lower with respect to the condition of the soil that is totally dry. That means that the suction is playing an important role in the stability. Here there is the video that is showing the evolution of the failure surface. You can see here this crack that is happening, so it's totally different, the shape of the failure surface, while in the dry parts tend to follow the initial, the one of the dry that I've seen in test 1. Here there is the digital imaging correlation, again in terms of vertical displacement, horizontal displacement, and the combination of them. And here you see that the failure surface is, in this part where there is suction, the failure surface is totally different with respect to the one of the dry one. And here there is the combination of the two things. So the next step that I'm going to do is to simulate the rainfall event with these huge head showers to simulate the infiltration. I will do the test with a SILT soil to see which is the impact of the rainfall on this kind of material and how it's changing the lateral air pressure. Then on the first part of my presentation is regarding the numerical analysis. The first results that I'm going to present here are relating to a case study of gravity retaining wall, where this is the initial configuration where we have silt soil that is, we have a drainage system and the wall with the drainage inside him. I'm considering three scenarios: an operative scenario, the condition where the drains are clogged, and if no drainage system is placed, is considered. So what I did first, I've considered the two extreme rainfall events, actually really short and intense rainfall events, and a long and less intense event, to see what happened. I started to model this problem, fixing boundary condition and the infiltration route, doing the refining of the mesh in this part. And then I was performing the uncoupled hydromechanical analysis with some hypothesis for the moment on the constitutive model that is linear elastic, linear perfectly plus with an envelope of more Coulomb failure criteria. And then I start to do the analysis, performing the 2' 3' reduction to see what happened to the failure surface. Here there are the input parameters of the two materials that I consider, of course, are the one that I studied in laboratory. I was pretty happy to see the failure surface of the analysis, and in this video is showing what happened to the matrix action during the rainfall events, how it's reducing, how it's increasing in this part, especially this part that is rising up. And you can see here also the deformation of the wall. And with this approach, respect to the analytical one, we could have an estimation, a measure of the factor of safety, and also a measure of the displacement of the wall for all the scenarios that I was considered. We have that the factor of safety is reducing with the time, and the lower part that was close to the failure is we got, of course, for the condition of the wall where the drain were clogged. And the rainfall events that allow us to arrive to where we got the highest displacement were the one with the long but less intense events. So after 12 hours we got the maximum displacement and also the minimum factor of safety. So with this part we have the opportunity, I will say, to use the unsaturated soil mechanics to design a retaining wall. But we have to see how can we say from an environmental point of view if we would like to consider the environmental impact, how much we can save if we use the mechanics of unsaturated soil. So with the industrial partner, we have implemented the life cycle assessment model. The life cycle assessment is an analytical tool that helps to take into account the impacts on the environment, starting from the extraction of raw material up to the disposal scenario. So we were comparing the three types of soils has a retained soil for retaining wall, considering the unsaturated design approach by all the things that using all the approach that I've shown you before, with comparing to the case where the wall has been designed and considered the soil totally saturated with groundwater table at the top. And the results of the analysis have shown that actually the impact depends from type of soils that we are retaining. There is a significant increasing of the silt soils where the matrix action has the highest impact. And so we have a reduction of the 40% in terms of human health, climate change, resource consumption, and ecosystem quality. While for the sand, for example, we don't get any kind of improvement. Moreover, I would like to say that the recycling of the materials play a non-negligible role, especially in terms of human health, where we are performing the analysis, the life cycle assessment analysis. So as main conclusion, I would like to say that the water retention behavior and the characterization of the water retention behavior play a crucial role where we are using the mechanics of unsaturated soils in classical geotechnical problems. The experimental analysis have confirmed the reduction of the lateral thrust and the significant change of the failure surface with respect to the dry condition. Seepage analysis must be performed in order to evaluate the changing in pore water pressure in the retaining soils. And also I can say that we have analytical and numerical tools. Also, all of you are now experts on unsaturated soil mechanics, so that means that I would like to say that the unsaturated soil mechanics play a crucial role in the challenge to have a low carbon future. And thank you for your attention.